So what I want to do today is talk to you about another operational amplifier circuit called an integrator. You'll notice here that we have now a capacitor which is connected from the output back to the inverting input. This is going to be an ideal integrator, and what we need to do is determine what this output voltage is as a function of this input voltage over here. Now the way we're going to do this is very similar to what we've done before. We're going to define a current in this direction. We're going to call that current I1. We'll define a current in this direction. We're going to call that current I2. So let's write equations down for both I1 and I2. All right, well the current I1 is equal to, now let's think about this for a moment. Okay, the non-inverting input here is actually attached to ground. Assuming this output voltage over here is not in a saturated condition, we're then going to assume that this point over here is a virtual ground. So voltage-wise, this is also at 0 volts. So this current I1 then is simply equal to the voltage V in divided by that resistance, which is R1. All right, let's write down an expression for the current I2. Well, I2 is equal to, now if you remember, current and capacitance and voltage, I is equal to what? C dV by dt. So this I2 then is equal to the capacitance C dVO by dt. Okay? So we've got basically a VO voltage which is going to be across that capacitor. All right, now let's look at these two currents, I1 and I2, and we'll sum the currents at this node. We're assuming no current is going into the actual op-amp itself. So we can actually say then that I1 going into the node plus I2, which is defined as going into the node, is all equal to 0. All right, what does that mean? Well, it really means that I2 is basically equal to a minus I1, taking the I1 to the other side. So now let's put this information, I1 and I2, into this equation. So if we do this, I2 is going to be what? C dVO by dt being equal to I1, well there's a minus there, it's an inverting amplifier, so there's a minus V in divided by our resistance R1. Okay, now taking C, or dividing both sides by C, we can say that we have dVO by dt is going to be equal to minus, what have we got here? 1 over RC, that's R1C multiplied by V in. Okay, let's rewrite this now as dVO as being equal to a minus 1 over R1C V in dt. Okay, let's integrate both sides here. So what we have is then integral of dVO is equal to minus 1 over R1C integral of V in dt. All right, now let's look at our limits over here. We're going to say that our limit for VO would be the initial value of VO, so I'll call it VO at time 0, all the way up to a value of VO at time t. And then our limits of integration over here would be simply 0 and t. All right, let's see now if we can actually perform this integration here. So what do we have here? Performing this integration here, we simply have VO. And VO, of course, is going to be between the limits of VO value at time 0 and the VO value at time t, okay? And that is, of course, equal to a minus 1 over R1C and we're integrating between 0 and t the input voltage dt. All right, let's take this just one more step here. We're going to put in these limits over here. So putting in those limits, we have what? We have VO, okay, at time t, minus the VO, that's the initial condition, at time 0, is equal to a minus 1 over R1C, integral from 0 to t, V in dt. Okay, let's assume that this value of the output voltage at time t is equal to 0 here. We'll assume that that is equal to 0. So let's assume then that VO times 0 is equal to 0. So now we can rewrite this equation as VO, as a function of time, is equal to a minus 1 over R1C, integral from 0 to t, V in dt. And as you can see, basically the function V out is really what? It's an integration, or it's the integral of the input voltage with a constant sitting in front of it. Okay, so this is really what we're calling the ideal integrator. Okay? Now, I want you to think with me here a little bit, okay? I've got a capacitor that's connecting the output back to the inverting input. Now, if the frequency over here is, let's say, equal to 0, then basically the impedance of that capacitor is going to be what? It's going to be infinite. And so effectively now, we really don't have a connection from that output back to the inverting input. What that means is that if we have a small voltage here, very, very small voltage here at this node, with respect to this node over here, it means that this output is really going to go into a saturated condition. And so we might find then that V out is basically going to be in a saturated value. So really this circuit over here, yes, an ideal integrator, but it really is not practical. And if you were to build this, you're going to find this output really sitting in a saturated value. A solution to this problem is to actually place a resistor R2 across that capacitor, such that when V in, or when we have, let's say, a DC source or zero frequency, we do have a feedback path through R2 back to the inverting input, stopping this guy over here, this output voltage, going into saturation. So now what we'll do is we'll see if we can analyze this circuit, come up again with an expression for this output voltage. We'll treat it much the same way as before. So let us define a current here. We're going to call that current as before. We'll call it I1. Let's call the current in the capacitor over here. We're going to call that current I2. And the current in this R2 resistor, we're going to call it I3. All right, let's write down expressions for these currents. All right, the I1 current is simply going to be equal to, once again, this is a virtual ground, output not in saturation, so we're going to call this V in divided by the R1 resistor. The current I2, well, that's the current in the capacitor, just as before. This is C dVO by dt. And then, of course, the current I3 over here is going to be equal to this output voltage, VO, divided by the resistance R2. What else do we know here? Well, we can sum these currents at this node, and we can say that I1 plus I2, because they're all defined as going into that node, plus I3 all equals 0. So if we rewrite this expression, then we can say that I2 plus I3 is simply equal to a minus I1. Okay, let's put in these values. So we'll put this into here, we're going to put this guy into here, and we're going to put the I1 into here. All right, doing that, what do we get? We get I2, which is C dVO by dt, okay, plus VO divided by R2 is equal to a minus I1, which is this V in divided by the R1 resistance. All right, let's multiply throughout by the resistor value R1. Okay, so if we do that, we get R1, and we get C dVO by dt, plus we've got an R1 divided by an R2 times VO, and that is equal to a minus V in. Think about this just for a second here. All right, we want this to behave like an integrator. Now we've got that R2 resistance that has been incorporated. So what we're going to do is we're going to basically make that R2 resistor considerably greater than the R1 resistor. And by considerably greater, we might be 10 times bigger, we might be 100 times bigger than the R1 resistor. So what does that do? If I'm making this guy big with respect to the R1, it's really making this term over here very small, okay? So that term becomes very small in this equation, and what we're going to do is we're effectively going to neglect it as it's a very small term. So what we now have is really what we had in the ideal case, and if we simply basically divide both sides by R1C and take the dt to the other side, what we have is dVO is really equal to 1 over, there's a minus sign there, the R1C times V in dt. And so if we now integrate both sides, so we'll integrate here, we'll integrate over here, the limits of integration as before, we're going to have a value of VO at time 0, a value of VO at time t, and limits of integration over here will be simply 0 and t. All right, so performing the integration here, what do we have? Same as really before. We have basically VO between these two limits, VO at time 0, VO at time t, and that is of course equal to a minus 1 over R1C, limits between 0 and t, V in dt. If we assume then the value of VO at, as we did before, at time 0 is a 0, then we can simply write this expression down as VO of t is equal to minus 1 over R1C integral from 0 to t V in dt. And so this then really is the same function that we had in the ideal case, except we've got that R2 resistor which stops that output really going into a saturated condition. This is a practical version of that op-amp integrator.